Welcome to the third module. We will continue our explorations with the oscillations of the loaded string, a system of connected particles. And we also saw that we do not have to be specifically worried about boundary conditions until we get the equations of motion. But when we want to solve it for a specific case, we need to put in some boundary condition to be able to get some suitable results. And here if you look at this equation, this is the equation of motion, and we have assumed that there is uniform tension T in the string, and R tells you which particle you are looking at. It is the index for the particle. So, you have n particles and R will go from 0 to n plus 1. So, there are n particles ranging from 1 to n. The 0th particle at one extreme end and the n plus 1th particle at the other extreme end will not oscillate, they are tied to the walls. So, that in some sense is also our boundary condition. And to solve this equation of motion, we assumed solutions of this form A r e power I omega t, where omega is the normal mode frequencies that we wanted to determine. The entire system will oscillate with one frequency. You cannot have a situation, at least in this kind of cases, where one part of the system, or let us say half the particles oscillate with one frequency and another half oscillate with another frequency. That cannot happen. So, here is a picture of the system that we are looking at. I have two rigid walls, and 0th particle and n plus 1th particle is embedded in the wall, and rest of the n particles are free to oscillate strictly in the vertical plane. A0 is the amplitude of the 0th particle, A n plus 1 is the amplitude of the n plus 1th particle, and with all these assumptions and substituting in this solution, we derived the results being one is the normal mode frequencies, which in general is given by this one. For a n particle system, n normal mode frequencies, this j is essentially a index for the normal mode frequencies. So, j goes from 1 to n, okay. J 1 would mean the first normal mode frequency and so on. And r, as I said, is the index for the position of the particle along your string. So, A r would tell me what is the amplitude of the rth particle, and again the amplitude of the rth particle depends on which normal mode you are looking at. So, the amplitude A r depends on both the indices r and j, as you can see here. And this general expression for the normal mode frequencies omega j square, which is here, can be simplified if you are looking at only the lower frequencies, which means that j is much less than the number of particles that you have. In that case, we saw that we can write that omega j is equal to j times omega 0, where omega 0 is this quantity, pi by L multiplied to root of T by rho. Rho is often called the linear density or mass per unit length. With this background, we will address a few related questions related to this problem. So, the first thing we should do is to see if all that we did is right. So, we already solved for example, a problem with two beads. So, suppose I have this simple system, instead of considering n particles, my n is now 2. So, this is the 0th position, n plus 1th position, or maybe I should say 3rd position, and this is 1 and 2. We solved this problem already in one of our earlier modules. We know the results. Now, we should check, now that we have derived a more general case, we should check if we are still able to reproduce those known results from these general results. So, if I have this problem, in this case n is equal to 2, and I am going to have two normal modes. So, j will run from 1 to 2, and there are 2 particles. So, R will also run from 1 to 2. So, let us see if we can first get the known results. Let us first get the normal mode frequencies. So, I have this expression that we derived earlier. So, I just need to plug in all the values. So, if I do that, so let us first get the lowest frequency. So, I have this expression 1 minus cos pi by 3, and if I set j to be equal to 2, which will be the second normal mode frequency, that would correspond to omega 1 square equal to 2 t by m a 1 minus cos 2 pi by 3. So, I will leave it to you as an exercise to substitute the values for cos pi by 3 and cos 2 pi by 3, and you should be able to recover the known results for omega 1 and omega 2. Now that we have the normal mode frequencies, let us see if we can get the normal modes themselves, the pattern of oscillation. To get the normal mode pattern, we need to work with the expression for the amplitude, which is given by this expression. So, now we will repeat the same exercise. So, let us set j equal to 1, which means that I am going to get the normal mode for the lowest frequency, and in the normal mode I want to get the amplitude of the first particle. So, that would mean that R is equal to 1 as well. So, now simply plug in all these things. So, I will get A 1 is equal to C sin pi by, of course, n is 2. So, that is pi by 3. Now, what about A 2? So, there are 2 particles, and again we are still looking at the lowest frequency corresponding to j equal to 1 and now R equal to 2. So, that would give me C sin 2 pi by 3. Sin pi by 3 is equal to sin 2 pi by 3. Therefore, we can write A 1 is equal to A 2. So, this is our normal mode, or if we write it in vector form, this will be 1 1. So, that is our normal mode. Now, so we look at the second normal mode corresponding to the larger of the frequency. So, that would correspond to j equal to 2, and again I will work with do it for the first particle corresponding to R equal to 1. So, in this case the expression would be, and now I stick to j equal to 2, the same normal mode, but for the second particle. So, now it is easy to verify. Again you can put in the values for sin 2 pi by 3 and sin 4 pi by 3. You will notice that A 1 is equal to minus A 2. So, that would correspond to saying that my normal mode is 1 comma minus 1. Okay. So, again if you remember what we had done in the previous module, these correspond to 2 distinct patterns of oscillations, one in which the 2 particles just go up and down like this together, the so called in phase oscillation, and the other one where when one of the particle is above the equilibrium point, then second one is below the equilibrium point. So, you have this anti-phase oscillation, when one goes up the other goes down and so on. So, that is this second mode. So, if I have to quickly sketch that, it would correspond to something like this, whereas the first one would correspond to something like this. So, in general we kept arguing that if you have n particles, you should have n normal mode frequencies. Can we say something about what is the largest frequency that is possible? So, let us address that question. Now, I need to determine what is the maximum normal mode frequency that is possible. It is easily seen from the formula that if this quantity is equal to minus 1, that is when omega j would be maximum, and that would happen if j is equal to n. In other words, we are looking at the largest mode. So, the frequency of the first mode is the lowest, call it 0th mode, and the next one has higher frequency and so on. So, the nth mode should have the highest frequency. So, I am going to set j is equal to n, in which case omega n will be equal to 2 pi by m a into 1 minus cos j is equal to n pi by n plus 1. And of course, if n is sufficiently large enough, you could sort of say that in the limit when n is much greater than 1, n by n plus 1 is approximately equal to 1, in which case this whole thing simply boils down to 2 t by m a into cos 1 minus cos pi, and that is simply equal to 2. So, this would just be equal to 4 t by m a. So, my result says that omega n square is equal to 4 t by m a, and this can be written as 4 omega 0 square. Hence, omega max or the maximum frequency possible is equal to omega n, which is equal to 2 omega 0. So, this quantity 2 omega 0. So, if you remember, omega 0 is the lowest frequency possible for your system, and the largest frequency possible in your system is simply twice the lowest frequency that is possible, 2 omega 0. So, this is called the cutoff frequency, and this is true in general for this class of systems. So, when I say this class of systems, it means systems which are in one dimensions, like the one that we are considering, and the particles are periodically arranged. So, if you consider this class of systems in one dimension periodically arranged particles, then this cutoff frequency 2 omega 0 is a common result for all such cases. So, we have seen what is the largest frequency that is supported by our system. What about the normal mode itself? What is the pattern of oscillation corresponding to this largest frequency? This can be obtained by again going back to the equation for the amplitudes. So, just to remind you once again, the equation for amplitude depends on two things: one, the normal mode that you are looking at, and the position of the bead along the string. So, just to fix the parameters, so I am going to look at the normal mode corresponding to the largest frequency. That means that j is equal to n, and of course, r will go from 1 to n. A 0 and a n plus 1 as usual are equal to 0. And this quantity c sin r j pi divided by n plus 1 can be rewritten slightly differently. It can be written as c sin r into pi minus beta r, where this quantity beta r is equal to r pi by n plus 1. To get some information about the pattern of oscillation, I also need what is a r plus 1. Let me for comparison also write a r, which will be c sin r pi minus beta r. Remember that r is an integer going from 1 to n. So, if a r is sin r pi minus beta r, a r plus 1 comes with sin of r plus 1 pi minus beta r. So, in other words, if r happens to be a odd number, r plus 1 would be a even number, or if r is a even number, r plus 1 would be a odd number. So, under all these circumstances, if I take a r plus 1 divided by a r, the ratio will always be negative, simply because one of them is always going to throw up a negative sign for a given value of r. So, which means that the neighboring amplitudes are always going to be negative of the other. So, there is always going to be a negative sign in this ratio of a r plus 1 divided by a r. So, with all this information, now we can roughly plot the pattern of oscillation, and we can in general also look at what is the overall profile of these oscillating particles. To do that, we just need to go back to the formula, which is the ratio of the rth and r plus 1th amplitude, which is written down here. Again, in the limit when n is large, I will take n divided by n plus 1 to be equal to 1 approximately. So, I have a r to be approximately c sin r pi, and when r is 0, which is this point, and r n plus 1 is this point. So, both are points at which the amplitude is 0. So, which means that this should describe for me an overall profile that is like this. So, this is for the alternative sequence of particles, which might probably be something like this. Now, you can do a similar analysis for a r plus 1, and it will tell you that the equivalent profile might look something like this, and that would correspond to particles here. So, now you can draw the overall picture. So, the alternative particles in this are always out of phase by pi with respect to each other. The neighboring ones maintain a phase difference of pi. So, this more or less completes the coupled oscillator system. In the next module, we will look at how we can take the limit when the distance between the particle goes to 0 and go to the continuum limit.